Welcome to section 3.4 on limits at infinity and horizontal asymptotes. So before jumping right in, we have this limits at infinity, an investigation here of it. If you let f be the function defined by f of x is equal to x squared minus 1 divided by x squared plus 1, where x becomes large. So I have the table here on the left and the graph on the right depicting the same concept. At 0, the function becomes -1. And as we start going to increasing values of x, we could see our function value for this particular thing increasing a bit, but it starts approaching a number that we could start seeing, especially down here towards the bottom. And that's both with the positive numbers and also if we start approaching negative numbers as well. And we could see that going on in the graph here, right? The blue line here is the blue curve is our graph, and you could see it approaching on the right towards this positive one, and also approaching an, positive one as we let x be large. And if we let x be large negatively, we could see that the function's approaching 1 as well. So because of that, we could say that the limit as x approaches infinity, meaning x becomes very large, x squared minus 1 divided by x squared plus 1, it approaches the value of 1. Likewise, if we let x be large negatively, so approaching negative infinity, the limit as x approaches that negative infinity of x squared minus 1 divided by x squared plus 1, that is also equal to 1 for that same exact reason. So a limit at infinity. If you let f be a function defined on some open interval from a to infinity, then the limit as x approaches infinity of f of x is equal to L, means that the values of f of x can be made arbitrarily close to L by requiring x to be sufficiently large. Or we could write f of x approaches L as x approaches infinity. So I have 3 graphs showing that on here, right? We have y is equal to L in the pink on here, and blue is the function curve. You could see that as we let x be large, in the positive direction, it starts approaching that value of L by increasing towards it. This second one here has the function approaching L as we let x be large by decreasing towards it. And then this one here has the function here approaching L. We could see at various points on there as we start getting closer and closer as x increases and becomes large, it starts approximating that much, much better. Likewise, with negative infinity, if you let f be a function defined on some open interval again, negative infinity to a this time, then the limit as x approaches negative infinity of f of x is equal to L. That means the values of f of x can be made arbitrarily close to L by requiring x to be sufficiently large negatively. So we could see as we make x be a large negative number, blue function here approaches that value of L on the left-hand side here. And same thing with this second one here too. We approach that value of L. So that line y is equal to L is a horizontal asymptote of the curve y is equal to f of x. If either the limit as x approaches infinity of f of x is equal to L, or the limit as x approaches negative infinity of f of x is equal to L. So we could see that going on in this example. I have the finding the limit as x approaches infinity of 1 over x, and the limit as x approaches negative infinity of 1 over x. So to find the limit as x approaches infinity of 1 over x, right? We could see it here on the graph, right? As we move towards the right and let x be large, this graph starts approaching that value of 0, which means this limit is indeed 0. But it's also important to make note that, if we start letting x there take on bigger and bigger values, we could see the fractions get progressively smaller, as I just drew on here for 10, 100, and 1,000 as 1/10, 1/100th, 1,000th, respectively. It starts approaching that value of 0. Likewise, as x approaches negative infinity, right, we could do that same thing. 1 over negative 10, 1 over negative 100, 1 over negative 1,000. So as we let x be large in the negative direction, we could see that the graph also does, as it shows on the graph here, approaching the value of 0. So evaluating limits to infinity, let us refer to this as theorem number 4. If r is greater than 0 is a rational number, then the limit as x approaches infinity of 1 over x to the rth power is equal to 0. Likewise, if r is greater than 0 is a rational number such that x to the r power is defined for all x, then the limit as x approaches negative infinity of 1 over x to the rth power is equal to 0. So with that being said, example 2, we want to evaluate the following limit and indicate which properties of limits are used at each stage. And I have the graph down over here as well to help us see this. But we have the limit as x approaches infinity of 3x squared minus x minus 2 divided by 5x squared plus 4x plus 1. We are going to first, before actually evaluating this limit, we are going to divide both the numerator and denominator by the largest power of x. Largest power of x in the denominator. So in this case, we're going to divide by x squared due to the denominator. So let me physically write those. So this is the same thing as the limit as x approaches positive infinity of 3x squared divided by x squared makes it 3 minus x divided by x squared is 1 over x minus 2 divided by x squared just stays the same, divided by 5x squared divided by x squared makes 5 plus 4x divided by x squared is 4 over x plus 1 over x squared. So doing that allows us now to calculate this limit, right? And based on those limit rules, so what we're going to do is from rule 5 of those limit rules, we could take the limit now of each part of that, so the numerator and the denominator. So limit as x approaches infinity of 3 minus 1 over x minus 2 over x squared divided by the limit as x approaches infinity of 5 plus 4 divided by x plus 1 over x squared. And by those limit rules numbers 1, 2, and 3, we could break this up even further to find the following. The limit as x approaches infinity of 3 minus the limit as x approaches infinity of 1 over x minus 2 times the limit as x approaches infinity of 1 over x squared all divided by the limit as x approaches infinity of 5 plus the 4 times the limit as x approaches infinity of 1 over x plus the limit as x approaches infinity of 1 over x squared. So by that theorem 4 we were just looking at, along with the limit rule number 8, we can evaluate these. So we're going to have a 3 minus a 0 minus a 0, well, 2 times 0, still 0, divided by 5 plus 4 times 0 plus 0, which will give us a nice, lovely value of 3/5, or 0.6, which is what the graph with the pink line on here is trying to represent. That's part 1 of this limits at infinity. Please be on the lookout for part 2, and let me know if you have any questions or concerns.